So I want to change flavor a little bit. So I want to talk about applying sums of squares and tropicalization to problem and extremal graph theory. And so if you were at workshop number 2, where Fernando talked about flag algebras, this should be somewhat reminiscent. But if you weren't, and this is completely new for you, please do stop me and ask questions, especially if you are a grad student. Please don't be shy to ask any question that comes up. So this is joint work with Greg, who just spoke, Mohit Singh, who's at Georgia Tech, and Rekha Thomas, who's at the University of Washington. So let me recall an old theorem from extremal graph theory. This is Mantel's theorem from 1907. If you've taken a combinatorics class at some point, this is something you might have seen, which states that the max number of edges in a graph on n vertices with no triangles is the floor function of n squared over 4. So what is this really saying? So this is saying that if, for example, I have this complete bipartite graph where the parts are as equal in size as possible, then this is where the maximum is attained. So I have n vertices. I have, if I look at any 3 vertices, I don't have a single triangle, right? So either I have 3 vertices on the same side, and then I'm fine, there's no single edge, or I have 2 vertices on one side and 1 on the other side, and I'm still missing at least 1 edge. So I don't have any triangles whatsoever. And what is the number of edges there? Well, it's roughly n over 2 times n over 2. And let me just zoom out a bit. I am in a weird way. So the total number of edges, okay, roughly n squared over 4. And I could have had n choose 2 edges, and I don't have any triangles. And so now I want to restate that in terms of densities. And so if we want to speak about densities, then we need to have some agreement on what we mean. And there's different types of densities. So one type of densities you might know is the subgraph density, where I'm looking at all injective maps from some graph from the vertex set of some graph to the vertex set of some other graph. So here, okay, my first vertex can go to any of the 4 vertices in G. My second vertex can go to any of the remaining 3 vertices in G. And my last vertex will have 2 choices of where to go to. So the total number of injective maps will be 4 times 3 times 2. And then I want to look only at maps that send edges to edges. And so if I count, I'll see that, okay, well, I could send, for example, my top vertex to my top left vertex. And then, okay, I'll have 2 choices of how to send the 2 legs. Either I send the left one to the top or to the bottom, and vice versa for the other one. Or I could send my top vertex to the, let's say, the top right vertex, and then I'll have more choices, right? I can either go the top line and the diagonal line, or top line and right line, or diagonal line and right line. And each time I have 2 choices, depending if I send my 2 legs of my path of length 2 like this, or if I flip it. Then there's the induced density, which is, if you saw the flag algebra talk, this is really what people were talking about there. So induced density, the only difference is that, yes, I'm looking at all injective maps, but I only want to consider the ones that send edges to edges and non-edges to non-edges. So for example, I would not be able to send my top vertex to my top left vertex, because then if I send the legs of my path of length 2 in any way, I get an edge there in the middle, right? So my non-edge that I have here becomes an edge there, and that's not acceptable. So here I'll have way less maps at work. I really can send my top vertex to my top right vertex, and then to these 2 opposite points, or vice versa, and to the bottom one. And so I went quickly over these because I don't actually really care about these ones. The one that we'll care about today is the homomorphism density. So the homomorphism density is different. instead of looking at all injective maps, I'm going to look at all maps from the vertex set of my smaller graph to the vertex set of my bigger graph. So maybe just to make sure we're all on board, in the chat, can all the grad students put how many maps will there be? And it's okay if you get it wrong. So I want to count the total number of maps from the vertex set of my path of length 2 to my graph, to the vertex set of my graph G. And now, of course, I cannot see the chat. I am not a WebEx expert yet.
So you might not.
Are there answers, Evelyn? Or
No, not yet.
Oh, okay. Oh, I see it appear upstairs. Okay, that's cool. So I saw it pass quickly. So there was one guess. So 4 to the 3. Does everybody agree with that? Or are there anybody who disagrees? So 4 to the 3 is correct. So I can send any of those 3 vertices to any of these 4 vertices. So I have 4 choices for each vertex, so 4 times 4 times 4 is 4 to the 3. Okay, so that's a total number of maps. Now I only want to keep maps that are homomorphisms, so that's send edges to edges. So now I have to be careful because, yes, I'll have all the maps that I had previously for the subgraph density, so those 2 times 2 plus 2 times 6, but then I can also consider maps that are not injective that send edges to edges. So I have my path of length 2, and these 2 edges can be sent to one edge. That's completely fine, right? So my bottom 2 vertices might be sent to the same vertex. As long as there is an edge there, I'll be fine. So anybody in the chat wants to venture a guess for how many maps send edges to edges here? Or if anything is unclear about what I'm asking, please do ask. So Kashkeli guesses 26. Anybody says more? Anybody says less? So far we've only gotten right answers, which has never happened before. But we didn't get many answers too. So yeah, 26 is right. So I have the 16 maps that I had before, and now I can send to any of my edges in G my 2 paths, either like this or the other way. So I have 5 edges in there. So for each edge, I'll have 2 ways of sending it, depending on which edge it is. So I have my 16 plus my 10. And so that gives me 26. Any questions about homomorphism density in particular? So all these densities are actually related. So the subgraph density is really just a Möbius transformation away from the induced density, or the flag algebra type of density. And the subgraph density and the homomorphism density, if you're looking into graphs where the number of vertices goes to infinity, well, they're really giving you the same information, because then if the number of vertices of G goes to infinity, this goes to 0, so the difference goes to 0. So they're all related. So the results I'm going to tell you about, you can think about them in terms of the other types of densities. But one advantage of homomorphism density is that multiplication will be nicer, and you don't have to look only at the case where the number of vertices of your graph G goes to infinity. So we'll stick to homomorphism density. but just keep in mind that we can translate some results. All right, so let's reformulate Mantel's theorem in terms of densities. So there we had that the max number of edges in a graph on n vertices with no triangle is n squared over 4. So that's really saying that the homomorphism density of an edge within any graph G is at most 1/2 if the triangle homomorphism density in that graph G is 0. And so now we're starting to see, oh, we have, okay, some inequalities. And so in the end, many problems in extremal graph theory really just boil down to certifying inequalities involving graph densities. And we know how to certify inequalities in the real world, right? We like to use sums of squares, and that's what we're going to be doing here too. But so before we go there, I kind of just want to maybe just give you a bit of a taste for really the bigger problem is what happens if you try to understand all valid inequalities that involve graph densities. So this is the concept of a graph profile. So let's say that I give you a list of some graphs, H1 through HL. These are finite graphs. Then the graph profile of this list of graphs is just going to be the closure of all the vectors of densities, of these densities within some graph G. And so I just take these vectors for all possible graph G, and then I take the closure of these vectors. And so this gives you some shape, and these shapes are pretty complicated. So here is like one of the easiest cases you could think about is if my list of graphs is an edge and a triangle. So on my x-axis, I have my edge density, and on my y-axis, I have my triangle density. And so any point within my gray region, that means that I am arbitrarily close to the edge density, triangle density of some graph G. If I'm outside of the gray region, that means that there is no graph G that can come arbitrarily close to that point in terms of densities. So you can see Mantel's theorem on the x-axis, right? So Mantel's theorem said that if the triangle density is 0, so if I'm really on my x-axis, then the maximum edge density is 1/2. And I see the last point that I have within my region is 1/2. So that's kind of cool. Mantel's theorem is just there on the x-axis. If you know a little bit about combinatorics, you might like to know that complete tripartite graphs that have parts equal are over here. 4-partite graphs, 5-partite graphs. So every point along the little scallop-y edge, and so there's always more scallops. I didn't draw them all. So you keep having these little concave bits. And so you could try to think, okay, so I can think about what these constraints are. So for example, this is that the edge density to the power 3 minus the square of the triangle density is greater or equal to 0. And so I could write other polynomial inequalities here. We don't actually know that in general these graph profiles can be written as the intersection of countably many polynomial inequalities. We don't know that. We don't know that it should be almost everywhere differentiable. We know very little about them in general, but okay, sometimes you do have these polynomial inequalities. So how do we certify them? And so, okay, there's a question. Do you get the same graph profile if you consider only densities in the limits? So in the case of homomorphism densities, we can consider all graphs, either finite graphs or graphs where the number of vertices goes to infinity. If I wanted to talk about either subgraph densities or for induced densities, then I would want to look only at graphs where the number of vertices goes to infinity. Does that make sense, Daniel? So the question is, okay, I will want to certify such inequalities with sums of squares, or maybe rational sums of squares if that doesn't work. So I think all of you know very well already all these things I'm going to say about sums of squares in the real world, but let me go quickly over a few results just to make sure that we're all on the same page. So if I have a real polynomial, I would say that my polynomial is non-negative if whenever I evaluate it on any point of Rn, I get at least 0. And I say that a polynomial is a sum of squares if I can write it as the sum of finally many squares of polynomials, right? And we know that a sum of square is non-negative. And so, right, it's a nice way of certifying a polynomial inequality. If I just write it in this form, it's very hard to see whether this polynomial is non-negative, but once I write it as a sum of squares, it becomes very obvious. So it's a certificate of non-negativity. And so of course, we wish that all non-negative polynomials could be written as sums of squares, but we've known for a long time now, since Hilbert, that yes, not all non-negative polynomials are sums of squares. And so you might know that after that, Hilbert asked, well, maybe we're asking too much. Maybe all non-negative polynomials are rational sums of squares, right? So if we allow for rational functions instead of just polynomials in our squares, then maybe this will work out. And so this was proven by Artin in 1927. He did show that, yes, every non-negative polynomial can be written as a sum of squares of rational functions. And so it took quite a while for a first example of something that is a non-negative polynomial but not a sum of squares to be found. So it was found by Muskin, this famous example that I plotted upstairs, where this polynomial m of xy is non-negative, but it is not a sum of squares. And so now I want to see, how do these results hold in the world of graph homomorphisms? What can be done there? So how can sums of squares work out to provide certificates for polynomial inequalities involving graph densities? So I'll just call sums of squares of polynomials involving graph densities just graph SOS. So in 2011, the Hilbert type of result was reproduced in the world of graph densities by Hatemi and Narin, and they showed that not every non-negative graph polynomial can be written as a graph sum of squares. So this is not too surprising, right? What was more surprising was that they showed that not every non-negative graph polynomial can be written as a rational graph sum of squares. So they showed that the Artin result in the world of real polynomials does not hold in the world of density polynomials. So that is, one first difference. So you might think maybe sums of squares is not just the right tool for the world of densities, but we know that it's actually quite good. So Lovasagiri and Netzer-Tom showed that every non-negative graph polynomial plus any epsilon greater than 0 can be written as a graph sum of squares. Right, so if you're willing to be approximate, then you're going to be fine. You will be able to use the sum of squares method to solve your problem there. And so just like in the case of real polynomials, at first, the proof was not so constructive. And so there was not a clear example of something that was non-negative that couldn't be written as a graph sum of squares. And so with Greg, Mohit, and Rekha, we showed that this polynomial here is a non-negative graph polynomial that cannot be written as a graph sum of squares. And so what is more, we also showed that it cannot be written as a rational graph sum of squares, right? So this is actually a famous polynomial. It's part of the Blakely-Roy family, which is part of the Sidorenko's conjecture. And so all Blakely-Roy inequalities are known to hold. It's just saying that if I have a path of length 3, so if I look at any graph and I look at the homomorphism density of a path of length 3 minus the homomorphism density of 3 disjoint edges, then that's always going to be greater or equal to 0 in any graph. And so it turns out that we cannot do this with sums of squares or even with rational graph sums of squares, thus giving us first examples of what sums of squares and rational graph sums of squares cannot do. So for the rest of the talk, I'll try to tell you how we did this. I'll try to tell you exactly what is a graph sum of squares, right? So right now, it might be a bit unclear what a graph sum of squares looks like. So I'll show you.
Sorry, a question?
Yes, please.
So does it make sense to ask that a polynomial is positive? Let's say for any meaningful graph in which you can embed, let's say, the three edges, you can also embed, let's say, for this kind of graphs, does it make sense to ask that graph polynomial is positive, strictly positive, let's say?
I haven't thought about it. I think you can ask the question.
So I was just wondering whether this positivity, whether this notion exists or not, implies SOS, or it can also fail in this case.
Say that again, Kelly.
So you mentioned this result by Lovash, Szigeti, and Netzer Tom, right? So it looks a little bit like positivity, right?
Yeah.
So like if you start with a graph polynomial that is positive in a certain sense, let's say, that takes positive values, not just negative, but positive, then can you write it as a sum of squares, a graph sum of squares?
Yeah, no, that's a good question. I haven't thought about it. I do think, I feel that, I'm just trying to think if there's a clear example already that I can think of that will show that you'll always be able to get 0, right? So for example, if you were to send into a single vertex, right, you're always going to.
But yeah, I just want to exclude this kind of like non-trivial ones.
Oh, non-trivial ones.
After excluded, yeah, non-trivial ones.
Okay, well, with non-trivial ones, that I really don't know about it. I think, you know, like if you're starting to exclude some graphs, then it does become more interesting and harder to have a sense for me. But it's an interesting question, for sure.
Okay, thanks. Oh, Greg answered in the chat, so.
Okay. So any more questions before I start showing you how to do sums of squares in this world and tropicalization if there's time?
May I ask a question? Is this obstruction due to the fact that you have rational coefficients for the graph SOS?
So do you mean rational coefficients in the polynomial or in the actual sum of squares?
In the polynomial and the sum of squares.
So in the polynomial, it doesn't matter. So for example, I'll show you that I could have, I could put any coefficient, any non-negative coefficient in front of my homomorphism density of my path of length 3 whatsoever, and that would still not be a graph sum of squares or a rational graph sum of squares. So yeah, the rationality of the coefficient does not matter so much there. Here it can be any real coefficient in front of it, and I still won't be able to do it. Does that answer your question, Dana?
Yes, in some extent, but the graph SOS they have, so you don't assume you have rational coefficients. Yeah.
No, I could definitely have, you know, a coefficient of the square root of 2 would be completely fine, not a problem.
I mean, yes, rational coefficients times square of rational polynomials with rational coefficients.
Yeah, I'm not restricting to only rational coefficients anywhere.
Thank you.
Any more questions? Okay, so let me show you the tools that we need to understand sums of squares. So far, I've only shown you unlabeled graphs. And so sometimes it's going to make sense, and most of the time it's going to make sense to have partially labeled graphs and understand what that means in terms of densities. So whenever I'm going to have a partially labeled graph, what it means is that I'm going to mean that my labeled vertices go to a particular place within my my target graph. So my target graph is really unlabeled, but I give it labels in the sense of I know where the labeled vertices are going. So I'm only considering maps that send vertex 1 to this vertex that I'm naming 1, but which is really unlabeled. Vertex 2 to vertex 2, and so on. So here I'm looking for the homomorphism density of my partially labeled graph into my larger graph. And so, well, only my unlabeled vertex can go anywhere, right? So my vertices 1 and 2 have to go some predetermined place. So my unlabeled vertex, there's 6 places where it can go. And out of the 6 places that it can go, well, it could go to vertex 3, it could go to vertex 4, and it could go to vertex 2, but it cannot go to vertices 1, 5, or 6. Then I wouldn't get that each edge is sent to an edge. And so the reason that I need to consider these partially labeled graphs really comes from representation theory. If I was only allowing sums of squares of homomorphism densities of unlabeled graphs, that would be like saying I can only use the trivial representation. I would not be able to use my whole decomposition. And that's why I need to allow for partially labeled graphs. And that's really just a point if you know some representation theory. Otherwise, it's really just, okay, to have the full power of sums of squares here, you really do want to include densities of partially labeled graphs, not just unlabeled graphs. Another tool that we'll use is symmetrization. So symmetrization really is going to be equivalent to unlabeling. I'm going to represent it by square brackets. And so really what it does is that, okay, so here I'm saying these 2 vertices are going to somewhere specific, and now I'm going to allow those 2 specific places to be anything. So I'm really going to be looking at sending this vertex to 1 and this vertex to 2, then this vertex to 1, this vertex to 3, this vertex to 1 to 4, and so on for any choices of vertices within my target graph. So in the end, I'm really going to be looking at any possible way of sending the vertices of an unlabeled graph into my target graph. And finally, the last thing that we need to know how to do if we want to do sums of squares is to do multiplication, right? We take a square, we need to know how to multiply. And so how it ends up working out is that multiplication is just gluing along vertices that have the same labels. If you get any edges that get doubled, then you just keep 1 copy and that's it, right? So if I multiply the homomorphism density of this guy with the homomorphism density of this guy, well, I just need to glue. I get this kind of little house without a bottom. And so this is where things change in terms of if you had subgraph or induced density instead. So if you had induced density because of the Möbius transformation, this would be some complicated expression. Not very complicated, but more complicated. And if you had subgraph densities, then you would want to say that this holds only for target graphs where the number of vertices goes to infinity, right? Because you would have to consider the potential of both vertices going to the same place or not. And the probability that they end up in the same place would go to 0. And so you would get the same thing as here. So these are our 3 tools. Any questions before we do an example with them? All right, so let's do an example and see if it all makes sense. So let's say that I want to show that the homomorphism density of a path of length 2 minus the homomorphism density of 2 disjoint edges is greater or equal to 0. So what will be my sum of squares proof for this? So it will be exactly this here. So it's going to be that 1/2 times the symmetrization of the following square gives me exactly what I need it to be. Just to be clear, symmetrization is really adding and normalizing. So this is really a good, like, honest to God sum of squares. So let's see how it works out. So I take the square of my polynomial. So I get the first term times itself minus 2 times my cross product plus 2 times plus the square of my second term. Then, okay, I know how to do multiplication. In my first term, I have 2 labels that are the same, so I glue them. In my second term, I don't, so there's nothing I can do. In my third term, I see that again, I have 2 vertices that are labeled the same, so I glue them. And then I can, I symmetrize, which is really the same as unlabeling. So my first and my third term become the same. So I have 2 times my path of length 2 minus 2 times 2 disjoint edges. And so I have 1/2 of that. And so it gives me exactly a path of length 2 minus 2 disjoint edges. So this is a sum of squares proof. Okay. And so we know that if I'm willing to go approximately, then this will always work. But we also know that if I really want to know exactly, this might be problematic. So I want to give you a feeling about what are the weaknesses of sums of squares here. But any questions about how the sum of squares work in this world? So Daniel asks, in Hasselbach's paper, you do get some factors when unlabeling graphs. Why do they not appear here? So this again comes down to the Möbius transformation. So the Möbius transformations make things messier in many ways. So somehow working with homomorphism densities just makes things so much simpler and cleaner than with induced densities. And then Marcus asks, why are squares non-negative? So it's because whenever I evaluate them, right? So you're right, so why are some negative? Once I evaluate them on any graph, they're going to be non-negative, right? So once I evaluate any expression that I have on a graph, then I get some real number, and so then squares are non-negative, just as in the real case. Daniel and Marcus, does that answer your questions?
So I still have to think about it because there is this unlabeling and so on, but okay.
So the unlabeling really comes down to adding, right? So I'm taking like I'm taking my term that I have here, and instead of having 1 and 2, I'll have 1 and 3, and I'll have 2 and 3, and 2 and 4, and 3 and 5. So any vertices, so any pair of vertices, including the same vertices within my target graph. And I'm just adding these squares and normalizing, so dividing by the total number. So really, I am not doing anything weird at all here. I'm really taking a sum of squares. Monique asks, the multiplication of graphs is defined so that the density of product is the product of densities. So it's defined, so this was our multiplication, is the product of densities, the density of product. Monique, can you explain what you mean?
No, I probably missed the definitions, and because a graph polynomial for you, it's a polynomial in the densities, it is T of H. So that's,
Yes.
yeah. So
yes.
Then you define the product of two graphs.
Mm-hmm.
So this should mean something in terms of the polynomial. The polynomial at the end is going to be a polynomial in the densities.
Yeah, so here, I mean, I do use a shortcut, which I did not say, which is a very good point. So when I just write the graph alone, I really just mean the density of the homomorphism density of the polynomial. So yes, this is how you multiply homomorphism densities. And then when you deal with multiplication of polynomials, you really just do it the same way that you would normally do it, but in terms of the densities.
So your multiplication here means that the density of the house,
yes,
in any G is equal to the density of the first in any G times the density in the second?
Yes, exactly.
Okay, so that's what I meant with my sentence. Okay.
Okay, good.
Okay. Thanks a lot for clarifying. Thanks.
Well, thank you for your question, Monique. Any more questions before I show you the weakness of this method? Yes, I'm completely fine with not going into tropicalization or just giving you a brief survey. All right, so what is a weakness? So if you consider a homogeneous non-negative graph polynomial of degree d that can be written as a graph sum of squares, and by homogeneous here I mean that all of the density of graphs involved all have the same number of edges, then my polynomial p can be written out as a graph sum of squares where any two monomials in any given square multiply to have degree d. What this is saying really is that you won't get to cancel out terms with things of higher degree. So there won't be cancellations happening. So the statement is actually a bit stronger than that. What we actually show is that if you look at the lowest degree part of any graph polynomial, this has to hold. You won't be able to cancel things out. So because of that, it's not too hard to show what can happen. So for example, if I were to look at something of degree 3, so there's not many graphs with 3 edges. There's a triangle, there's a path of length 2 with an edge, there's a 3 star, a 3 path, and 3 disjoint edges. These are all graphs with 3 edges. And so, okay, if I think about the fact that any two of them within the same square have to multiply to degree 3, there will not be a lot of mixing and matching happening. And so I can write it out fully and figure out that these are the only sums of squares that exist. I have to have a polynomial that has this form. And so my M1, M2, M2, M3 need to form a PSD matrix. And so now I could think about, okay, so let's say that I want to have that I have one in front of my homomorphism density of my path of length 3, and I want to have -1 over here. Can I do that? And then it just turns out that I can't. So in that way, even if I put a to be any real number, so even if I make it even more non-negative, that will not work out. And so, as I said, this statement about how things don't cancel out is actually for the lowest degree part. So even if I were to multiply with a 1 plus a sum of squares, the lowest degree part would still be exactly the same thing. So it still wouldn't work out. I still wouldn't be able to find a sum of squares there. So not all rational sums of squares will have this form where I'm multiplying by 1 plus a sum of squares. But this was starting already to give us an idea that, okay, well, maybe sums of squares are not that good. And this was answering a question by Lovas. And so this ties into Sidorenko's conjecture, which is a big conjecture and extremal graph theory, which says that for any bipartite graph H, the homomorphism density of H minus the edge density to the number of edges in H is greater or equal to 0, right? So actually, this polynomial is part of it for when I have that H is a path of length 3. That's an example of it, which we do know is non-negative. But in general, for bipartite graphs, we don't know that this holds. And so for a long time, people were wondering if sums of squares or the Cauchy-Schwarz method was the way to solve this conjecture. And so, well, this is a homogeneous polynomial. And so clearly from our previous result, sums of squares will probably not be the right way. Already we cannot do it for this simple example, which was already known to hold. And so for the smallest open case of the conjecture, we show that that you cannot use sums of squares. So I'm pretty much out of time. So let me just tell you, there's a way of tropicalizing.
So Annie, sorry, but
yes.
You've been taking all the questions. So I think you can, happily go until, until 55 at least, or even slightly further. Huh?
Okay, well, maybe just, and I'll do it very shortly still, just in case there's more questions. So one thing that we were wondering is, well, are rational sums of squares, any better? And so an interesting object that came up for us to think about is tropicalization. And so tropicalization really just means taking the log. So we saw this object called the graph profile, right? This weird object that Hasbahov proved was correct for edge and triangle. So, okay, you have your vectors of densities, and you're going to take the log of every single component. And you can do it in any base that you want. And so the tropicalization, or the logarithmic set of your graph profile, is taking the limit of these logs of points and base 1 over k as k goes to 0. And so this is this weird object. And so the first thing that we did was to show that actually it's not that bad. You really can just see it as being the closure of the convex hole of the log of the graph profile. So it's a closed convex cone. Okay, so the big idea here is to say, I have this very complicated object that somehow, explains polynomial inequalities for graph densities, and I'm simplifying it to a closed convex cone. So for example, right, this was my very hard example of a graph profile, even in the case of an edge and a triangle. And so here is the tropicalization. So this object is much simpler. And so you might think, is it too simple? Well, yes and no. You do lose a lot of information, but what you still have is that you still understand binomial inequalities involving whatever densities that you have. So you're not trying to understand all polynomial inequalities that are valid. You're trying to only understand the binomial inequalities that are valid. This is what you're keeping. And a lot of problems in extremal graph theory involve only binomials. So it's not too bad. So we are able to describe the tropicalization for a graph profile of any number of complete graphs. It's very simple. I won't go through the details, but it's just, okay, you know, whereas in the case of graph profiles, we only have a few descriptions of a few profiles for 2 graphs, never for 3 graphs. In the case of the tropicalization, yeah, we can do it for examples with however many graphs as you want in certain cases, like complete graphs or complete hypergraphs and stars, complete hyperstars. Greg and I are working on paths. We're hopefully getting close. You can use that to actually solve problems in extremal graph theory, because as I was saying, a lot of them have involve only binomials. And so the other nice thing that, you know, a lot of you might care about is that you can use sums of squares to approximate this tropicalization. So a little bit like what Greg was talking about in his last talk, you know, we could look at the SOS profile, so we could look at all the points in our that make our moment matrix PSD, or we could look only at a 2x2 principal minors. So Greg was talking about NEK here. We're just talking about 2x2 principal minors. And so then we get this relaxation. So we have our graph profile, we have our sum of squares profile, and we have our 2x2 principal minors profile. And the 2x2 principal minors profile, that we can fully explain. That's a polyhedral rational cone that's we can fully describe. And so this gives us a way of approximating the graph profile, and sometimes it will be enough. And it is enough to help us understand better rational sums of squares as well. So with it, we come up with a way of finding a point that allows us to find something that is not a valid inequality for our biggest approximation of the 2x2 minors, and then showing that something is not a rational graph sum of squares. So this was very quickly, but really the takeaways are homogeneity is a weakness, both for sums of squares and rational sums of squares in the world of graph densities. So because of that, sums of squares might not be a best tool for some homogeneous problems in extremal graph theory, like Sidorenko's conjecture. So it won't be enough to prove them fully, at the very least. And yet, you know, there's this very nice object, which is a tropicalization that is very interesting, which is much simpler, but which still captures binomial inequalities. And given how many problems are about binomial inequalities, it's very worth it to study it. And so we do want to understand the tropicalization of graph profiles better. Every example that we've done has always led to a rational polyhedral cone. We can show many cases where it has to be a rational polyhedral cone, but we don't know that it has to be. So we would like to understand that better. It also pops up not just for graph profiles. You can do it, you know, like if for simplicial complexes, for matrices, and there you'll also get polyhedral cones. So we'd like to understand what is that property that guarantees polyhedrality there. We still don't know that rational sums of squares are better, stronger than sums of squares in this world. So we would like to find an example of a non-negative graph polynomial that is not a sum of squares, but that is a rational sum of squares. And well, for whenever sums of squares are weak, we do want to study other certificates, right? So for example, there's these sums of non-negative circuits. And so maybe they can offer strength whenever sums of squares are weak for these types of extremal graph theoretical problems. And so I'll stop here. Thank you, and sorry again for taking too much time.
So this was great. Thank you so much for taking the question on the fly. I think it really helped. So do we have more questions? I mean, there has been a lot, so, but do we still have questions? So I'll try to get the ball rolling with the question. So you said that there are many binomial inequalities about graphs. Are there some you could tell us about like that from
Yeah.
top
So
of your mind?
one slide that I went quickly over is this one. So there was this long-standing conjecture by Eldash and Simonovitz, which said that the number of homomorphisms from a path of length t, so with t edges, to the power s is greater or equal to the number of homomorphisms from a path of length s, so with s edges, to the power t, whenever s and t are odd and t is greater or equal to s. And so through the tropicalization with paths, it is easy to show that the conjecture holds. When we did this, we didn't know, but Netzaglam had already solved it in 2018 in a completely different way. But so this is one example. Siderenko's conjecture is another one, right? So I put Siderenko's conjecture. This slide, right? So this is again a binomial. Ramsey type problems, Durant type problems are also binomials.
Okay, thanks. Sorry, I missed this.
Oh, well, I was going fast.
Is there somebody else who has a question for Annie? Any question? Oh, Mattheus.
Yes, hello.
Hi.
Yes, so I have maybe a little more technical question. So you have managed to prove that this tropicalization is a polyhedral cone, but you don't know if it is rational. Is that correct?
No, so we don't know in general that it is a polyhedral cone. So we know that it's a rational polyhedral cone in every example we've done. We know that it is a rational polyhedral cone for anytime that you have series parallel graphs. So we do know big classes of graphs for which we can prove that it is polyhedral and rational polyhedral. And we do know that it is rational polyhedral for simplicial complexes and matroids. But for graphs in general, we don't know. And yeah, so is it polyhedral one? And then if it's polyhedral, is it rational polyhedral? And so this would have an effect on whether it is decidable, the validity of binomial inequalities is decidable, which is open. So we know that polynomial inequalities involving graph densities is an undecidable problem. But what about just a pure binomial inequality? We don't know. And so if we had polyhedrality in all cases, then we would have decidability.
Okay, and another question. Are these cones in your examples, are they happen to be also like tropically convex or no?
So they're not exactly this. So if you know a bit about tropical geometry, it's a bit different here. So like normally, in tropical geometry, you always have this. You have this line, right, in the 1, 1, 1 direction, which here we don't have. Here we just have the vector. So we only have it in one direction. So it's not exactly the same as what people talk about in tropical geometry, but it's very close.
Okay, I see.
So is it does tropical geometry occur in some other parts of graph theory or extremal graph theories?
I think I've seen a couple of recent talks where people do start thinking more in those terms, like not necessarily like close to the same line as what we've been doing, but yes, more and more, some people are starting to think about how tropical stuff can make certain things easier, right? Like they're tropicalizing always simplifies, like it, you know, for us, you know, like, okay, addition and multiplication becomes, you know, taking the max and adding. So you're changing what your operations look like, which can give new insight. Yes.
All right, thanks. Great. So I think we've gone through all the questions, it seems. Well, it was a fascinating afternoon. Thank you to both speakers. Thank you for the attendance. We had lots of attendance, so very successful. So, well, I guess I can tell you until next time, and next time is next Friday. So thank you all. Have a nice weekend, and see you from your home next time.